properties of solutions. Many of the mixtures that we encounter every day are actually mixtures. Whenever they're homogeneous, we call them solutions. So table 11.1 has various types of solutions that are in everyday life, but notice how there are gas, liquid, and solid all listed there. And that's because solutions can be made up of all three types of states of matter. Solution composition can be found in different ways. Mixtures have variable compositions, meaning qualitatively, dilute means that when we say a solution is dilute, it's relatively has little solute present, and concentrated is when it has a relatively large amount of solute present. And so concentrated and dilute are used to describe the solution content, what's in that solution. We first described solutions in chapter 4 with molarity, symbolized by the capital M, molar, for the unit, or the number of moles of solute per liter of solution. So that would be total volume of solution on the bottom. Another way to describe solutions is using what's called a mole fraction. And they use a cursive X, or the Greek letter chi, to symbolize that, where it's the ratio of the numbers of moles of a given component to the total number of moles of solution. So this equation is given to you in your equation sheet, but if you wanted to find the mole fraction of component A in this mixture or in a solution, then you would take the moles of A, N stands for moles, over the total moles of everything in the solution. So it might be 2 parts, it might be 3 parts, but you add up for the total on the bottom. All right? So example 1, we're going to use our molarity and our mole fraction. A solution is prepared by mixing 1 gram of ethanol, which is C2H5OH, with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity and the mole fraction of ethanol in this solution. Well, let's do the molarity first. Okay, so we know molarity is equal to moles over liters, but it's the moles of the solute over the liters of the whole solution, the volume of the whole solution. Okay, so we are adding ethanol into water. The way that you figure out what's the solute and what's the solvent here, the solute will always have less, the solvent will always have more. So our solvent in this case is going to be the water, and the solute is going to be the ethanol, C2H5OH. Okay, so we need to find the moles of this ethanol to put on top. So we know that we have 1 gram of ethanol to start. So we need to divide by the molar mass. And when you add up the molar mass for that, I got it to be 46.07. So then that would be, when you figure out the moles, 0.0217 moles of ethanol. I'm going to just put ETH for ethanol because that's shorter. Okay, so we're going to plug that into our equation on top. And then the liters of solution is the whole solution. So we want to know the final volume is the whole solution volume. Okay, but it needs to be in liters. So in order to get milliliters to liters, divide by 1,000 or move it 3 times left. So that is 0.101 liters. So when you divide that out, our molarity is, keeping it in 3 sig figs, 0.215 molar. Okay? Well, we're going to use some of this information to help us to solve for the mole fraction. So, cutting my paper in half. The mole fraction, we want to find the mole fraction of the ethanol. So we need the moles of the ethanol over the total moles. Well, we already know the moles of the ethanol because we solved for that just right over here. But we need to know the total moles. So that means that we need to figure out how many moles of water is in the solution. So we have 100 grams of water. and we're going to divide by water's molar mass, and that is 18.015. So the moles of water is equal to 5.55 moles of water. So to find our mole fraction of the ethanol, we are going to take our moles of ethanol, the 0.0217, over the total. So we're going to take the moles of ethanol again, but we're going to add the 5.55 moles of water. So the overall mole fraction is equal to, it's very small, 0.00389. Again, that answer is 0.00389. There's no unit on mole fraction because the moles cancel out the moles. And so that's it. Hopefully not too hard. Keep moving along. We also have what's called normality. Normality is very similar to molarity, but it's symbolized by the capital letter N. It's defined as the number of equivalents per liter of solution, where an equivalent depends on the reaction taking place in the solution. It actually depends on the number of protons in your solution. So for an acid-base reaction, the equivalent is the mass of the acid or base that can be furnished or accepted, exactly 1 mole of protons. So it's all dependent on the H's, basically, okay? And it has to do with how many H's you have. So if you have 1 H, this is kind of telling you, like for HCl, if you have 1 H in there, then the molarity is going to be equal to the normality, okay? But if you have increased number of protons, like the H2SO4, the sulfuric acid has 2, so then you would just need to know that the normality is twice that of the molarity, okay? Same thing with hydroxide. Technically, hydroxides have 1 H or 2 H's, right? But same thing with hydroxide for the base side. If you only have 1 hydroxide, you have 1 normality is equal to the 1 molarity. But if you have 2 hydroxides, the normality is doubled. Okay. So, in example 2, we want to determine the normality of the sulfuric acid that has a 3.75 molar solution. Well, sulfuric acid was just in our last table. It's H2SO4. And since it's H2SO4, that means that we have 2 protons present. Because we have 2 H's right here, right? So 2 protons is equal to the 2 equivalents. So that means that we need to multiply the number of moles by 2. And if molarity is moles in 1 liter, we're going to take the moles that we started with, which is actually 3.75 moles from the H2SO4, and we're going to multiply that by 2 because we have 2 equivalents. So that when you multiply that by 2, it's actually 7.50, and that's how many equivalents per liter you have. So that means that our normality is equal to 7.50, and then we just label it as an N. And then basically all you need to know is however many H's you have, if you know the molarity, you multiply that by that number of H's. It's not as daunting as it seems. Okay, so we can figure out the energies of solution formation. We encounter dissolving solutes and liquids in everyday life. What factors affect this? Well, like dissolves like is our most common thing that we need to know. Where that means, like when we saw in the chapter 10 simulations, the nonpolar and polar molecules didn't mix very well together. And so you need to have the same kind of intermolecular forces happening in order to dissolve. So the steps of formation of a liquid solution, you need to separate the solute into its individual components, and then it needs to overcome the intermolecular forces in the solvent to make room for the solute, and then that allows the solute and solvent to interact to form the solution. So this picture is on page 515 in your textbook, where it's showing you how we have the solute and the solvent have to expand apart in order to create space between them in order to make the solution. So where it says step 1 and step 2 in your picture, those are both expanding, meaning that it's gaining energy, so it's an endothermic section right there, until it condenses back down. And then in step 3, that would be an exothermic part of the combination. So each step of the process requires energy. The enthalpy change associated with the formation of the solution is called the enthalpy P of solution, or delta H solution, is the sum of the delta H values for the steps. So however many steps you have, that's what you would add together. The only thing is, the sign on the delta H solution may have a positive sign if the energy is absorbed, or negative if the energy is released. And that's where thinking about our thermodynamics is very important. So this graph shows us, this is also on page 515 in case you want to check it out. It shows us the heated solution where A, in picture A, the solution has a negative sign because the process is exothermic. And that's because the energy of the solution is lower than the energy of the separated solute and solvent. But for B, the energy of the solution is higher than the separated ones, and so because it's higher from the separated ones, then that would be an endothermic process, so it would have a positive sign. So that's kind of showing you pictorially in a graph how those are. Okay? Dissolving ionic solutes in water, specifically, we have what is called the enthalpy of hydration, or the delta H hyd, as I like to call it. Combines the terms of the delta H2 and delta H3, where we get this information. This represents the enthalpy change associated with the dispersal of gaseous solute in water. So we could calculate this out for sodium chloride, that's right here, where we are going to add together the two delta H's. This one, the one from the breakdown of the solid into gaseous ions, and then the heat of hydration. So, doing that, to find the heat of solution, we would take our 786 kilojoules per mole plus the negative 783 kilojoules per mole from the enthalpy of hydration, and so when we add those together, we get 3 kilojoules per mole left over. So this number is very small, but that means that the dissolving process requires a small amount of energy, so it will be very easy to dissolve. Something that would have a very high number for the enthalpy of solution would mean that it takes a lot more energy to dissolve, and so it's maybe not going to be a very good solute kind of thing. So it would be insoluble. Some other principles to consider quickly. One factor that favors the process is an increase in probability. Those process that requires large amounts of energy tend to not occur. Example 11.3 on page 517 talks about this, and it will help you with a few of the homework problems. So this is the end. Actually, I'm sorry, that's a typo. It should be table 11.3. My bad. I didn't include it in your notes though. So this is the end of the level 49 notes. Please refer to your checklist to know which problems to do for your assignment.